Hello, in this session today we will be diving deeply into the subject of time-varying coefficient regression. This specific methodology is quite important and it will serve as the final topic we explore within our extensive time series regression section of the material we're covering. Alright, as is our usual approach, we're going to work through a concrete example together, and we'll be applying this particular example directly using the resources available on the Finance Research Git website. Before we do that though, let's first thoroughly explore the foundational idea that truly lies behind the time-varying coefficient. When we're working with a simple linear regression model, meaning we have just one independent variable, x, our main task is to accurately fit a straight line to the data. This allows us to precisely estimate the slope of that line, which shows the change in y for each unit change in x. Additionally, we must also estimate the intercept representing the predicted value of y when x is 0.
That is something which is always constant and can be fully explained by x.
Any remaining component, any moving part that isn't adequately explained or fully accounted for by our independent variable x. That by definition will constitute our error term. And when we apply a simple ordinary least squares regression, this method will then provide us with just one single straightforward slope.
So there is one unknown fixed slope that we are going to estimate using the OLS method.
And this will be done for the entire data set. This is based on a fixed coefficient way of thinking. However, in numerous financial and economic applications, this particular assumption might not be very realistic because the underlying relationship between y and x, and indeed between all variables, tends to change over time. This could occur due to a financial crisis, shifts in regulatory frameworks, fundamental structural break, fluctuations in market volatility, evolving levels of market integration, the pace of market adjustment, or even evolving policy decisions.
All of these will indicate a modification in the relationship between y and x.
So, with ordinary least squares, we typically assume there's a single constant effect of x on y. However, a time-varying regression model suggests that while an effect of x on y does exist, this relationship isn't static. Instead, it can evolve and shift dynamically as the broader economic environment changes.
So, in our empirical example, the y variable would be the stock,
the financial return of a particular firm, and x would represent the market's overall return. Or you can take it in a different way, where the stock market's return is your y variable and the x variable is the world market's return. In any case, the coefficient that you estimate in your model will inevitably be time varying. It will certainly change over time. So, in this analysis, we're going to perform two main things. First, we'll estimate the beta coefficient for each period as it evolves over time, and then we'll model that specific coefficient within a separate second regression. Ultimately, this means we'll be working with two distinct regressions, the first one and the second one.
The coefficient here is a function of the lag value plus some uncertainty or error.
So, in our methodology, we permit the coefficient's value to not be constrained to a single exact or strict point. Instead, we actively account for and allow for a certain degree of inherent uncertainty within its modeling process. That V specifically denotes the measure of uncertainty associated with the intercept term in our model, and V1, in a similar vein, represents the uncertainty involved in accurately estimating the beta 1 parameter, which is, of course, the crucial coefficient that is directly attached to our x1 independent variable.
And this particular variable is distributed with a mean of 0, and it possesses a variance that we're calling Q. So what Q represents in this context is the variance associated with the inherent uncertainty present in the coefficient itself, and this uncertainty is fundamentally modeled as a process known as a random walk.
What we are essentially trying to communicate here is that the most reliable estimate for the coefficient is the one observed in the immediately preceding period. So, if we were to estimate the regression model, the specific value that we obtain from the most recent estimation period is then considered to be the optimal forecast for the coefficient of the subsequent period. And importantly, we also account for a certain degree of inherent error or some level of uncertainty.
So, the coefficient for today is equal to the coefficient from yesterday plus any new information.
Here in this analysis, we are looking at the key statistical coefficients. Specifically, we have the intercept value and the coefficient for beta 1. To manage this, we are utilizing the state vector, which is designated as alpha. The z values in this particular instance refer to the numerical coefficients. Specifically, these are the intercept and the coefficient for the x variable. Consequently, beta 1 is directly associated with or multiplied by x1. The specific value for our variable x1 is clearly presented right here within this particular vector, and then the corresponding intercept term is precisely defined by this singular numerical value, which happens to be 1. So, for example, if you were to multiply z by a, it's essentially like we're multiplying 1 by the beta 0 coefficient, and that will then give us the beta 0 value.
and then we add the quantity x, which is then multiplied by the coefficient beta.
And that is simply the linear regression that we have, connecting the x variable to the y variable. And that is the random walk, where the coefficient itself evolves over time, following a random walk based on its previous value. This specific equation is what we refer to as the Kalman gain, and its primary function is to enable us to accurately update the previously estimated coefficient. It's important to consider how things develop and evolve in this context as time progresses. Therefore, the specific data point or numerical value that we had observed or recorded previously might not necessarily remain identical. Furthermore, we possess the ability to incorporate or apply a particular kind of modification or adjustment to that initial historical value. This crucial adjustment, which plays a vital role in the system, is derived as a direct function of the Kalman filter, or more specifically, the Kalman gain. This particular updated adjustment is then subsequently multiplied by the existing error. So, when we are attempting to derive the predicted coefficient value for the upcoming period, our most reasonable and informed estimate is typically the very last coefficient that we previously obtained from our regression model, and to this, we then incorporate some form of necessary adjustment. That adjustment is a direct function, a consequent result, of the error that we observed during the most recent regression period. And then, we are going to have a new coefficient that is going to be predicted. It would be significantly easier if we considered a numerical example. Let's consider a scenario where at the conclusion of period t-1, which of course refers to the immediately preceding period, we had successfully derived these particular coefficients. Specifically, we found a value of 0.5 assigned to the intercept term, and then for beta 1, we determined it to be 0.8. I just want to emphasize that the 0.5 value is indeed for the intercept. That is specifically for the first beta version. And then we have to contend with uncertainty, a specific type of predetermined uncertainty that dictates we must allow these coefficients to flex. So, in essence, we grant permission for these coefficients to shift even before we have the opportunity to observe the actual error that will occur in the next period. The uncertainty associated with the coefficient beta 0 is found to be 0.04, and for the coefficient beta 1, the uncertainty value is 0.09. And that uncertainty, which is an inherent part of any measurement we take, has a very specific error term associated with it. It's officially known as the Q factor. For this particular case, we're looking at 0.01, and for that other situation, it's 0.04. And this assumption implies that when we conduct the regression analysis during the present time frame, specifically period t, you obtain an error term, and if we then compute the variance of this particular error term, this specific variance will serve to quantify precisely how large the error truly is, because the average value of the error itself is exactly 0. But if we take the variance of that error, it will clearly show us the extent of the spread or dispersion in the error term. It's just like when we perform the regression analysis in period t, specifically between our variables y and x. So, if we apply a rolling regression, for example, utilizing the most recent data period, and subsequently fit a trend line to that information, we will inherently encounter a certain degree of error or deviation surrounding that particular line. The distance between the error and the line, which is essentially the precise magnitude of that particular error, if it is then squared and subsequently taken as an average value, that resulting quantity would precisely correspond to this specific term we are discussing. That will give us the amount of the variance of the error, or the amount of the error, basically. Consider, for example, a scenario where we have a value of 0.2 or perhaps 0.25. Now, let's assume that our regressor value for today's observation is precisely 2, and the corresponding observed dependent variable is 3.4. We'll explore how the model accurately predicted the actual y value. Let's now examine the process of how that was achieved. If we proceed to apply this particular mathematical equation, we will then obtain a predicted numerical value that comes out to be precisely 2.1, a figure that, as you can clearly see, falls significantly below the true actual value. So the error that we observe here is positive, which indicates that the actual value is indeed higher than the predicted value by a margin of 1.3. Consequently, it appears that we have underpredicted the y variable based on the specific model that we are currently using. Once again, the model is presented with these coefficients, and it possesses an overall uncertainty that is equal to this specific number. To put it simply, what we did was take the Q value and combine it with the initial uncertainty that was already present in the system. This allowed us to calculate the total uncertainty for all of these particular coefficients. And what that implies is that, yes, we currently have a figure of 0.5 as
The intercept value that was estimated, which was simply derived from the final regression within the previous period's estimates, is now being utilized as the designated value for all of the coefficients that apply to this current period. We have a value of 0.5 for the intercept. However, that particular value may fluctuate, moving both up and down, influenced by the specific level. Similarly, 0.8 could also experience variations, going up and down, affected by the same level. The zero in the diagonal elements indicates how the uncertainty in the coefficient estimates, specifically between the intercept and beta 1, evolves over time. Here, we are assuming that there is no correlation in the uncertainty of the coefficient estimates. This means that if we see an increase in the uncertainty of one estimate, it is not related to the uncertainty in any of the other coefficients.
The most important aspect here is represented by these values.
And then when we determine the predicted value, as we are already quite familiar with, it's simply the beta 0 term, which is then added to beta 1, and that is subsequently multiplied by x1. This entire mathematical expression is precisely what this equation is designed to accomplish. We take the number 1 and then multiply it by the value of 0.5. This resulting product would then become the intercept that we are using as an estimated value for this particular period's coefficient, which is 0.5. So if we consider beta 1, its value is 0.8, and we're multiplying that by the variable x. Now let's assume for a moment that x is equal to the number 2. When we perform that specific calculation, it will result in... No, it's actually the other way around. You see, the beta value that we're considering here is 0.8.
If we multiply this by 2, the resulting calculation yields a value of 2.1. However, the actual true value is observed to be somewhat higher. This difference, therefore, constitutes the error term, which in this specific case is clearly positive.
So the actual y value is significantly larger than what the model had originally predicted.
So the primary question we're grappling with here is, how precisely are we going to effectively reflect that particular aspect within our model's parameters? With the ordinary least squares method, we typically utilize the entire time series data, we input this into the regression analysis, and ultimately we derive a single definitive number, and that's the extent of it. We handle this process period by period. For the final period, we typically get 0.5 and 0.8. However, we remain open and flexible, ready to adjust these values based on any errors we've identified. If the error count is 0, it means that no further adjustments are required, which would be perfectly acceptable. However, since we do have an error present, we must then proceed to ask the following crucial question. The fundamental question we're addressing here is, do we need to update these coefficients? And the definitive answer to that, unfortunately, is yes, because we've clearly identified an error. So the crucial follow-up question then becomes, by what specific amount should we adjust them?
We need to determine the precise amount by which we should revise the coefficients. In this specific case, we underpredicted the y value because the actual y was higher. So we must adjust these coefficients, whether it's the intercept term or the specific coefficient that is attached to our variable x1, which we call beta 1. The key question is by how much we need to revise these values upward. This is exactly where the Kalman filter or the Kalman gain becomes essential. Gain. And the Kalman gain, which is a very important element in this process, is primarily a function of something we call f. This f, to be more precise, is essentially the forecast error variance. It's the error variance, that's the main point, essentially. Pause. And that particular metric will then inform us about the degree of uncertainty with which we perceive or handle the error. So, the f variable, in this context, will effectively measure the extent of the uncertainty surrounding that specific surprise. What this means is, how much confidence do we place in this surprise, believing it to be a truly significant value that we absolutely must use to update the coefficients? If it's merely random noise, then we certainly shouldn't be paying any attention to it, indicating that it carries a very high degree of uncertainty. However, if that particular error is not purely random in nature, but instead it is a systematic certainty, which implies that we must then proceed to update our model, specifically its coefficient estimates, and consequently we need to apply a significantly higher Kalman gain value. Now, regarding how the f value is precisely calculated, well, it is determined directly by utilizing this specific mathematical equation. We plug the numbers in. Here we have the co-intercept value and also the coefficient. Apologies, not the coefficient itself, but rather x1, the specific value of x1, and then you multiply that result by the uncertainty associated with the coefficient. So when you multiply that value by 2, it's essentially like you're determining the overall uncertainty associated with beta 1. This represents the overall uncertainty, since we're considering 2 units of x. When this is multiplied by the uncertainty associated with a single unit of beta, it will then provide us with the total uncertainty for the coefficient beta 1, given a specific level of x's value. Same thing also applies here. It's the uncertainty or total uncertainty and the intercept. We're now going to take this particular quantity and multiply it once more by the relevant values that we've previously established. Upon completing this operation, we arrive at a sum of 0.57, which is then combined with 0.25. This specific value of 0.25 represents the standard deviation of the error term, a crucial component that we had previously discussed and introduced earlier in our explanation. This one right here. Do you recall the error component we discussed from the previous regression analysis? My apologies. I meant the one from our current regression model. This specific error component will play a very significant role in the decisions we need to make right now. That's because if we observe an excessive number of errors, it directly implies that we are dealing with a much higher level of inherent noise. Consequently, this gives us a clear and quantifiable measure of that underlying noise. And if we have a higher level of noise present, it clearly indicates that we shouldn't really place our full trust or confidence in the current error value that we have observed, specifically the error that we have actually seen as a positive error of 1.3. 1.3. However, if the overall noise level within our current regression analysis is quite high, then it implies that the resulting error term shouldn't be entirely relied upon or considered valid, indicating it's simply random fluctuation, not a meaningful pattern that we should attempt to model or use to adjust our parameters accordingly. So, by carefully combining these two crucial factors, specifically the inherent uncertainty along with the calculated regression error, we will then obtain the comprehensive total F value. A higher F statistic indicates that we cannot rely on the error term we observe within the current period's regression analysis, because it is merely random noise, irrespective of whether that noise originates from the current data point's specific regression, or from the permissible range of movement due to uncertainty and the various estimates of the coefficients. There's a prior condition, something established before the current regression period. Our focus now shifts to point 2.8. When we proceed to calculate the inverse of this particular value, a computation that is specifically going to be executed right here in this very step, the outcome we achieve will then be identified as the Kalman gain. Consequently, a higher value for f implies that when we perform the operation of taking its inverse, the resulting magnitude will inevitably become significantly lower. If we take 1 and divide it by 0.82, the result of that calculation would be 1.219. After that, we would then multiply that figure by the total amount. We must account for the inherent uncertainty surrounding the estimated coefficients, including the intercept term and the specific value for beta 1. When you do that, when you perform that operation, you determine the precise magnitude of adjustment needed for the coefficients, which is specifically called the Kalman gain. It's important to note that for our current analysis, we are required to adjust the intercept value, moving it upward by a precise amount of 0.06. Consequently, this particular situation indicates that our next step involves modifying the coefficient designated as beta 1, and subsequently, we must increase its magnitude significantly by exactly 0.317. So once more, the intercept will be adjusted by approximately 0.06 times the forecast error, and the slope will be adjusted by approximately 0.317 times the forecast error. So this is the Kalman gain. Regardless of what you have, whether it's positive or negative, if the error is positive, the adjustment will move upward since you multiply by a positive value. If the error that we are observing is found to be negative, you will then be multiplying by a negative number, and this means you will adjust the current estimates downward. So this is not the final value that is simply added into the intercept term directly. Instead, we must multiply it first, based on the error term that we calculated and subsequently found to be 1.3 positive. And then, once we've completed the multiplication by the error term for this specific period, we then add it back into the equation. So, what will be the final outcome? So, the Kalman gain that's applied to the intercept is currently set at 1.3. Because of this, we are now required to increase the intercept by a value of 0.07. And then, in addition to that, we also need to increase the coefficient. So, for the beta 1, we initially had a value of 0.419, but then it was revised to 0.412. So, considering our original coefficients, the intercept, which was initially at 0.5, we then take the specific number and add it directly to that value. This calculation will then give us the brand new intercept. You can see now that it's higher at 0.57. So initially, the coefficient for our variable x1 was recorded as being precisely 0.8, but then, following the analysis with the new period regression, we found it necessary to adjust that coefficient. We actually increased its value by 0.41, and consequently, the updated figure is now 1.21. So it became higher because of the positive error, and that positive error is not entirely just a noise. This object holds some relevant information, and based upon that commonly understood equation, we made the choice to adjust the coefficients, shifting them upward so they would then align with these precise values. So prior to actually observing the new data, we initially held the belief that the slope would remain consistent with our previous period's regression analysis. For instance, we thought it was 0.8. This value, 0.8, represents the coefficient of x1, which is beta 1. Yes, it's beta 1.
And once again, this is the beta 0 value we have prior to any adjustment.
When we saw that the value of y turned out to be considerably higher than we had initially predicted, this directly led to what we call a positive error in our calculations. In other words, our forecast was too low. We significantly underpredicted the outcome. Following our recent calculations, we have successfully revised the slope and its current value is now set at 1.2. Therefore, the newly determined coefficient beta 1 has been established as precisely 1.212. So the relationship between x and y has now become significantly stronger than it was previously. Now let's apply this concept within the field of financial research. For this, I will be using time series data. We're going to use a monthly setting for this, and then we will carefully select the entire period that needs to start from the year 2000, and then it will run all the way until the year 2024. Once we click apply, it's essential that we proceed to the next step. At that point, we'll begin to construct what we call series A. This particular series A is going to represent our Y variable, and specifically, it will be defined as a firm's stock return.
So the variable is the one that is monthly. Stock return.
Right, we're going to select just one particular company. We'll then proceed to search for Microsoft. Therefore, I'll input its ticker symbol, which is MSFT. After that, I'll press the enter key and then click outside the box.
Then make your selection from here.
Then go ahead and apply.
I definitely prefer to rename it myself, so I won't be using the automatically assigned default name.
So I will name it as Microsoft Return, click outside the box.
We are going to have two separate x variables for this task. The very first item we're discussing here is the overall market return.
And we are going to make a very careful choice.
We're focusing on the same specific variable. However, our approach involves aggregating that data by utilizing the median value across every single firm that's currently available within the entire market. Therefore, for any given month, we might be looking at approximately 3,000 or even 4,000 firms. Our process involves calculating the median value for each successive month. Through this approach, we are effectively discovering what we can consider a genuine market representative monthly return. Consequently, we maintain these boxes as empty. Therefore, by default, we include all firms that are part of the given sample, and then we simply proceed with the application.
I'd like to rename it to market.
You must return. So the final variable we'll consider in this analysis is the lagged firm return. This particular variable will be designated as x2 for our model. We won't be generating this specific data point within this current section. Instead, we'll simply utilize the data we previously established and created during our work in Series A, specifically the Microsoft stock return. Our immediate task is to proceed directly to the lag box creator, which is more commonly referred to as the lag creation box. Once there, we will carefully select the specific option labeled Microsoft Return from the list. Subsequently, we will formally submit a request for the system to incorporate exactly one lag. So we are in the process of creating a new variable, and this new variable specifically captures the 1 month lagged return for Microsoft.
All right, so now we're working with 3 columns. The first one is our Y variable, which represents the Microsoft return.
The second column represents the market return, which is x1, and the third column, x2, is the lagged Y variable, specifically the lagged Microsoft return. Once that's been incorporated, then we'll be completely prepared. Our next step will be to delve into regression-based time series models, which represents the very last subject we'll explore within this current section. The specific model we'll focus on is the time-varying coefficient model, more commonly referred to as the Kalman filter.
Well, the variable y represents Microsoft's stock return, which is the endogenous variable in our model. The exogenous variables include the overall market return and the previous period's Microsoft return. So at this point, we're now looking at the variable q, which is something we've already talked about in our previous session. Do you recall our earlier discussion about the specific q variable, which fundamentally represents the inherent error within the overall uncertainty measurement? This implies that the degree of variability within the uncertainty itself, pos and this factor, will consequently lead to an augmentation of the overall imprecision associated with the initial coefficient estimations. So higher uncertainty will reduce the Kalman gain. So we have to set this, and let's go with the same number, but let's increase it to 0.01. This indicates that the beta coefficient is experiencing drift. How are we allowing this beta value to change and drift over time, even before considering any new error terms? So even if the error term is 0, the beta parameter is still permitted to adjust and evolve over time. This is precisely the meaning of Q. So even before we proceed with the new regression and before we observe the new error that arises, we still allow the beta parameter to adjust in a particular direction and by a specific amount. And this adjustment is fundamentally governed by the Q.
And the noise, which was becoming increasingly disruptive, started to really bother everyone. So for this particular term, we are able to establish its value. And considering an average scenario, the noise level might be approximately 0.01. You're certainly able to either add to this or increase it further should you desire. Once these two crucial parameters have been defined, then we will be completely ready to proceed. We can then proceed to fit the regression model.
You should give it some time.
And here we have the calculated coefficients, which are not just for one single isolated period. It's that they represent every individual monthly period over the last 20 consecutive periods.
So if you observe this particular instance, for example, the coefficient associated with x1 representing the market return initially stood at 0.6. However, it's clearly evolving over time and its value is steadily decreasing.
Regarding the lag of Microsoft stock returns and the lag of the variable y, it is also steadily declining over time. So the Kalman filter is able to update its coefficients recursively as new information becomes available. And this process allows the researcher to effectively track how various financial relationships evolve and change over a period of time. This particular observation holds true, for instance, when considering the lag return effect. The situation is clearly deteriorating for our firm, Microsoft, and this downward trend is also evident in the broader market's overall returns as well, despite the fact that we've observed some intermittent periods of growth and positive movement. However, when we consider the overall picture, the prevailing trend is undeniably one of decline. So our analysis indicates that the market's overall influence on Microsoft's financial returns has been consistently declining over an extended period of time. And with that, we've reached the conclusion of our session for today. I truly appreciate each and every one of you for taking the time to listen.